Just had to
Oh,
do this.
thank you so much.
Sorry.
Oh, sorry. Thank you so much. Yeah. That's very important because yeah. So I so the I guess I didn't miss out too much. So basically, I'm just trying to say like a set of expectation for you guys about today's lecture, and how is what's the best way for you guys to to learn today's lecture. So basically, what I'm trying to say in that today's you can consider it's a parallel knowledge to what we learned in the topic 10. So today's lecture, instead of trying to infer our data, trying to infer the population characteristics based on our data, we are trying to first we formulate a certain question, and then we're trying to test whether our guess is correct or not. So it's similar it's similar to the previous lecture, but we're trying to use a different framework to do to fulfill our task. So, like I said in the beginning of the course, I won't expect you to do the mathematical derivation for this today's lecture. I just need you to understand what we are doing in the hypothesis testing, and I just need to understand what's the knowledge behind today's lecture. So when we talk about hypothesis testing, I will first like to just talk about the testing itself, and which involves quite a few terminologies. So when it comes to the testing, I don't know what kind of things that come up to your mind, but at least for me, I would think about the COVID-19 test. So like when we're trying to test for whether an individual is infected with COVID or not, we will use a certain like a swab to get some tissue or substance from the nose, and then based on that tissue, we kind of take it to the lab and to get some results to see whether this individual is positive or negative. Probably you guys has more expertise than me about this, but that's pretty much the idea about testing. But honestly, for almost every test, the test could be wrong. They could be make mistakes, right? So there's no say a perfect test or something like that. So in reality, we always expect that there could be some discrepancy between our test results to the actual results. So in fact, we can use what we learned in the lecture 8, where we learn about the two-way table to express such kind of discrepancy. So as we can imagine, our test results could be either positive or negative, and the actual results can also be positive and negative. So in this case, we could have 2 times 2, which is 4 different combinations of our test results and the actual results. So in this way, we can summarize all of this different combination in this 2 by 2 table. So this two-way table is actually quite uh, similar to the assignment question where uh, for the data set 8, we are studying like uh, what's the what's the party in 2016 and what's the party in 2020. So as we can see that for these two variables, the categories are the same. They both are either positive and a negative. So although these categories are the same, but you need to understand their meaning is different. So this positive is just referring to the positive in the test results, and this positive is just referring to the actual results. So in this way, we can express our, we can collect the data and to just record how many times each combination appeared, and we express this in the 2 by 2 table. As you can imagine, when we get a positive test and it is actually positive, which means it's a really nice thing. So it's good because our test is correct. And however, if our test is positive, but this individual is negative, then we make mistakes. And for when our test is negative and we get and we actually are positive, then that's another type of a mistake. And also, if both our test and actual results are correct, and then that means this cell is a correct cell. So as you can see, we kind of classify our cells into either correct or incorrect. But in fact, uh, although there's like a two cells that they are incorrect, but we can understand this incorrectness of these two cells differently. So as you can see in our COVID-19 example, if our test is positive and actually this person is actually negative person, and in that case, this mistake will probably make this person quite stressed out, right? And it will it will cause a lot of anxiety for this individual, so which is quite bad. But on the other hand, it probably will make this individual more cautious and just to keep more social distancing with the other individuals. So maybe this mistake is not so severe if we considering that. However, if we look at this mistake, the story will be different, because if we test a negative this for this individual, but in fact this individual is a positive one, and in this case, because he didn't know he is a positive one, right? Because according to the test, he got it a negative result. So he just keeping meeting new friends, and it's kind of just spreading the disease away. So as you can see, although we have a different mistakes, but their influence could be different. So trying uh, to differentiate the difference, we use the different names for them. So basically, we called the first type of the error as the false positive, because we test as positive, and which is definitely incorrect. And the second one is the false negative. So basically here, the positive and negative is according to our test results. So we're always talking about our test results. And similarly, we could define the another two cells, which are actually correct. And because they are correct, so they are true. And according to the test results, we classify as true positive or true negative. And here, I also would like to emphasize that the values here in each cells are just the counts. So when we talk about what's the true positive in the COVID-19 test, you will come up that, okay, that kind of statement is referring to like what's the count of the combination of the positive in the test and the positive in the actual results. Okay, any question about this? So let's do an exercise. So based on this 2x2 table, what is the false negative value for this COVID-19? So just remember, when we talk about negative and positive, we are referring to the test results, right? And just to look at whether the test results is aligned with our actual results, we decide whether it's true or false. Okay, I think we get a quite diverse results. Okay, so first of all, we're talking about negative, right? And this negative is corresponding to the test results. So which means we're looking at this row. And because we're talking about false, right? So when what type of the outcome is false? The positive one is the actual results, which is not the same as our negative one. So this one is the false. So that's why the answer is actually 10. So which is actually very straightforward, right? So we start with start with the test results and to check whether it's a true or false, which means whether our actual results is aligned with our test results to see. Okay, and another very important idea is that sometimes we don't talk about the counts, and we care more about the percentage. Like say if our false negative is say is 100, but if our total count is say 10,000, then probably we will very comfortable with this test. So usually we just knowing the count itself is not good enough. We care more about the percentage. So in this case, we will define the two different terminology according to the percentage of the true positive and the true negative. So sensitivity is a conditional percentage of the testing positive condition on the actual uh, positive results. So just fresh up your mind when we study in the lecture 8 that we see that we always start with like what's the event and what's the condition. So when we define sensitivity, our event is the testing positive and our condition is the actual positive results. So which means if we look at the conditional distribution, we will look at the first column. And then because we are talking about the event of positive, so we kind of look at the percentage of this cell among this column. So that's why the sensitivity is calculated by the true positive divided by the true positive plus the false negative. And sometimes in the literature, you probably encounter other names like a true positive rate or recall, but they just referring to the sensitivity. And similarly, we could define the specificity, which is the percentage of the testing negative condition on the actual negative results. So, so in this case, because our condition is actual negative results, so we're looking at the second column and look for the event of the true negative. So similarly, we can define the specificity. So just keep in mind that the sensitivity and the specificity are both the percentage of the truth, right? So sensitivity is the percentage of the true positive and specificity is percentage of the true negative. So here come up the question, like, do we want our sensitivity and specificity to be high or low? We, according to what I just said. So remember, both sensitivity and specificity are referring to like what's the percentage of the truth, right? So what do we expect? So the answer is A. So this is just very straightforward from what I just said, because you know the sensitivity and specificity, they both like the percentage of the truth. So we just want it to be as high as possible. However, we also need to keep in mind that in reality, sometimes although we want this, but it could be unrealistic to keep both as high. So sometimes we have to trade off between the sensitivity and the specificity. So just like the COVID test, in this case, we will take care more about the sensitivity because we are afraid of the false negative than the false positive because we know that the false negative has a probably wider impact in our general population. So if we have to choose between the sensitivity and a high sensitivity and a high specificity, we will just trying to make sure that at least we will have a high sensitivity in our COVID-19 exam. So any questions so far about the test and the confusion matrix? So why the denominator of the specificity? Oh, I'm sorry. This is actually a typo. So so because we are conditioned on the actual negative results, so the denominator should be false negative plus the true negative, or false positive plus the true negative. Thank you for catching that. So this is a typo over here. Yeah, good catch. Any other question? Okay, so I guess after understanding what is the some concepts about the test, um, in this in the beginning, then we kind of prepare for the hypothesis testing in the following lecture. Okay, I get a follow-up question. So it is Tn plus Fp. That's correct. So it's Tn, so which is this cell, plus Fp, which is this one. That's correct. Okay, so just quickly review like what we covered in the previous lecture. And when we talk about the statistical inference, we say that basically what we are trying to do is that we are trying to guess what is our parameter population, the parameter of the population, which is usually considered as unknown. And because it is unknown or it is very expensive to get, what we did is we collect some information uh, according to a sample, and then we calculate the sample statistics. So in the previous lecture, we gave the example of the average time that students spend in the course. And I also asked the iClicker question, if you remember, that whether the X bar and the mu should be equal or not. So definitely, and as we all agree, these two values should be different, right? Because we have certain variation in our sample, and basically these two are not the same individuals, right? Although our sample is a subset of the population, but they are not the same individuals. So we should expect the value should be different. However, in this lecture, I'm going to ask a different question. So instead of just asking, will these two average be equal or not, I'm asking, will these two average be equal statistically? So you might ask, what do you mean by statistically? So basically what I mean here is that, okay, I acknowledge that our X bar should be different from mu for sure, because we have a variation in our sample mean, right? But as you can imagine, if we acknowledge this sample variation, so if the difference of X bar and the mu is too small, and sometimes we can just ignore that difference because we know that's just out of the randomness. So the question, by asking the question of equal statistically, we mean that whether we can ignore this kind of small sample error, and if the sample area is so small that we can ignore that. So that's pretty much the question that we are trying to ask for today. So to answer that question, we are going to go through the hypothesis testing procedure. So first, just for an analogy, so just imagine we got a suspect, and we kind of suspect that this individual committed a certain crime, and we bring him to the court. And so what's the process of a trial is like, first of all, we just assume this individual to be innocent, right? So that's the usual procedure for a trial. And then we will ask our jurors to collect the information and to see whether there's some evidence uh, to to support or to against that the person is innocent. And finally, based on our materials or our evidence we have, we will make decision about whether this person is guilty or not. So the pretty much very similar idea in the hypothesis testing. So we start with a certain scientific question. Like in this example, we're asking whether our sample mean is equal to the population mean statistically. And based on that question, we first assume that our individual is innocent, which means we just assume this, okay, this is true. And then we're going to collect our data and to do some summarization and to see whether our assumption is correct or not. And finally, we will make decision based on the evidence we find. So that's pretty much the procedure that we have in the hypothesis testing. So as you can see, hypothesis testing, in the hypothesis testing, hypothesis is a very important part. And we consider this just as a very standard procedure and to testing a certain hypothesis about our population parameter. So in that case, our procedure of the hypothesis testing will be always standardized into 4 different steps. So first, we always start with a certain statistical hypothesis. We just assume that our because we want to ask for some some scientific question. So at first, we just assume you are right. We just assume that is true, and then in the step 2 and 3, we're going to collect the information and to construct some value to help to make the decision. So specifically, we're going to construct the so-called the test statistic. And further on, we will introduce the idea of the p-value, which is associated with the test statistic we have to help us to make the decision. And finally, we will make the conclusion just according to the p-value we have. So that's the procedure, standard procedure for the hypothesis testing. Any question for the procedure so far? Okay, I have some question about the final. So I'll talk about the final in the end of this lecture. Okay, any question just about the procedure? So because that's the pretty much the thing I require for this lecture. So just make sure that you understand the procedure of this. Okay, if nobody has any question, so we will go over each step one by one. Okay, so first we look at the first step. What about the formulating the statistical hypothesis? So as we can, as you know, when we formulate the hypothesis, our goal is to formulate the hypothesis for our research question, right? So when formulating the hypothesis, we usually have 2 different results. Either our initial question is right or our initial question is wrong. So the null so we will introduce 2 different hypotheses, the null hypothesis and the alternative hypothesis. The null hypothesis is referring to the case where our original assumption is correct, and alternative is just the complementary part of our null hypothesis. So as you can imagine, for the null hypothesis, there could be different ways to formulate our hypothesis based on our research question. So like in our example, we are looking for whether our sample mean is different from the population mean or not. So we just formulate that our null hypothesis is there's no difference at all. And sometimes we might interested whether like our sample mean is greater than our population mean or not. And in that case, our null hypothesis will be modified accordingly. And in the lecture 7 and 8, where we study the relationship between the variables, and in that case, we could formulate our hypothesis about the relationship or not. And so the take-home message for this part is that the null hypothesis is usually coming up from our research question. So based on what we're trying to look for in our research question, we will formulate the null hypothesis accordingly. So the alternative hypothesis is usually considered as the counterplot for the null hypothesis. So if we talk about no difference in the null, and we will look for defect in our alternative one. And if we look for greater than in the H null, and then we will look for not greater than. So just pay attention that in an alternative hypothesis for this greater than, we are referring to not greater than because it contains 2 different scenarios. Either it is smaller than or it is equal than. So there's a 2 possibility that in this not greater than hypothesis. And similarly, for the no relationship hypothesis, we will look for whether there is an association between our variables. Okay, any questions so far? Okay, if there's no question, and there is another thing that you need to know about the alternative hypothesis, that is, our alternative hypothesis could have two different types according to the hypothesis, the specific hypothesis we have. For example, for the different, so if we look for whether something is different, it's actually a two-sided test. Because, for example, when we say we want to look whether our sample mean is different from the population mean. So we are actually looking for whether our sample mean is smaller than the population mean, or the sample mean is greater than the population mean. However, if we look for like not greater than for this hypothesis, then we are actually looking for a one-sided test, because we just look for whether our X bar is smaller or equal to our population mean, which is mu over here. So after discussing or introducing the idea of formulating a hypothesis, now let's try to do an exercise. So like before, this exercise will be in a discussion with two or three students. So just like before, if you don't want to join the discussion, that's okay. You can stay in the main session and just to figure out the question on your own. So the question is like, remember in the first slide, the mean score of midterm 3 is around 16.57. And for this midterm, we have 144 students took the midterms. And suppose if I have the information for a general Western student who have taken this course before, and based on the historical results, I know that the average score of the same midterm should be around 16, and with the standard deviation of 2.4. So my research question is, do the students in this course have the same average score in our population statistically? So basically the population here means the general students who have already taken this course before, and also of course including you, because I'm considering you as a sample of this general population. So the task for this discussion is to figure out what is the sample that's in this example, and accordingly, what's the sample statistic and what's the population parameter that we're looking at. And then based on this information, trying to figure out what's the null hypothesis and what's the alternative hypothesis, and also look for whether it's one-sided or two-sided. So I'll give you approximately 8 minutes to think about this question, and we will get back at 2:12. So I'm going to break out into different rooms. So yeah, I'll talk about the question later after finish the task, okay? Okay, one more minute. Okay, since everyone is back, let's get continue. So, does anyone want to share their results, the of thoughts or discussion? You can just open your video or your um, just unmute yourself. Any volunteer would like to share? Yeah, that's okay. So, so first of all, I would say, I'm sure in the final there will be one question, like give you a certain context, and then you need to figure out what's the sample or the hypothesis underlying the context. So make sure that you understand what we're talking about for now. So in this case, I guess the sample is actually what we learned before, right? So the sample is the units that we're collecting data. So here, because we are collecting data from all the students who take the midterm 3, so our sample will include all the students that covered in the midterm 3. So the sample statistic here we are looking at is the mean, right? So that's the sample statistics. And accordingly, the population parameter will be the mean for the general population. And the null hypothesis is coming from the research question that we are trying to ask. So in our question, we're trying to ask like whether the average of our students is the same as the average of general population. So that's exactly our null hypothesis, that we assume that that's true, that the sample mean is equals to the population mean. And the alternative one will be just taking the complementary part of our null hypothesis. So in the null, we talk about is equals to. So the alternative is not equal to. So that's very simple, right? So remember that when we talk about like there's a difference or it is not equals to, this type of the hypothesis is actually a two-sided hypothesis, because either our sample mean could be greater than the population mean, or our sample mean could be smaller than. So just keep in mind that this is actually a two-sided hypothesis. So coming back to the question in the chat, so there is a question asking why is greater than um, also related to no difference. So I wasn't saying that the greater than is related to the no difference. So what I'm trying to say is that when when we're trying to formulate the hypothesis, our hypothesis should just coming up from our initial research question. So if we are interested in whether two things are equal, then we should, in our hypothesis, we should assume that is equal, which means no difference. However, if we modify our question, like if I want to see whether the students in my class has a greater average score than population, and then in that case, we need to formulate our null hypothesis by the greater than. So it's usually aligned with our initial research question. And I'm not saying that these hypotheses are equivalent with each other. So, so another message is that always make sure that our alternative hypothesis should be the complementary of our null hypothesis. So that's the things that we need to make sure. Okay, any question for the activity or the example? So make sure you understand this, okay? Because I will say there will be a question asking like what's the null hypothesis and whether it's a one-sided or two-sided for the alternative hypothesis in our Fiverr. So make sure you
Sorry.
understand.
I have a question, actually.
Yeah.
I'm wondering why the sample wasn't just everybody. Oh, never mind. Sorry.
Oh, because like the sample is the units that we are collecting data, right? So for this example, so all the units that I'm actually taking data from is all the individual or all the students who took the midterm, right? For those individual who didn't take the midterm, they should be non-responder, right? Because
Understood.
they didn't didn't give me the data. So that's the idea when we define sample. Does that
Okay.
make sense to you? Yeah.
Yes, thank you.
Okay, great. Any other question? Oh, can I show the answer for alternative hypothesis? Okay, so the alternative hypothesis for this example is just taking the complementary to our null hypothesis because our null hypothesis say equal to. So alternative one should be not equal to. So that's the idea when figure out. So as you can see, once you figure out the null hypothesis, and automatically you will figure out the alternative hypothesis. Okay, so there's a question about one-sided and two-sided again. So when we talk about one-sided or two-sided, we're usually referring to the alternative hypothesis. So for example, when we say A is different from B, right? So this type of the hypothesis is two-sided because when we say two things is different, there could be two different ways to make them different. So either our A is smaller than B or our A is greater than B. So that's why we call it a two-sided. So you can imagine our population is the population parameter mu is something in the middle, and our statistic x bar could be on the first side, on the left side, which is smaller than that, or on the right side, which is greater than that. So that's the idea that we call it two-sided. And the one-sided is just referring to the alternative, looking for like a greater than or smaller than, something like that. So in this case, we only have one region to look for, right? So when we look for not greater than, we only consider like whether our x bar is smaller than mu, and we're not worried about the other side. So that's why we call it one-sided. And similarly, in this example, because we're talking about not equal, so there's a two possibility. So our average could be greater than the population, and or we could smaller than. So both cases could be different, but so that's why it makes our situation to be a two-sided problem. Okay, so this is the pretty much the first half of the lecture. So like I mentioned in the email, so I will leave you around 15 minutes to work on the feedback of the course evaluation. So as I said, this is my first time to teach the course, and I'm very happy to have you guys to be my students. And I do learn a lot from you, and like in the office hour and in your discussion in the forum, which helps me to learn a lot from like how to teach and how to communicate with students. So it will be very helpful to give me some feedback so that I can take it for the future, and I will really appreciate that. And I assure that I won't see your response until your final results is it's get. And all of these responses anonymous, which means I cannot identify the students at all. Okay, so we will take a break for 15 minutes, and I will also send the link through chat so that you can quickly get access to it. So we will be back at 2:45, and you can also take a break. And after the break, we'll talk about the remaining procedure of the hypothesis testing. Hello, everyone. Let's get continue. If you happen still working on that, I think you can save the what you have, and then you can come back after the class. Okay, so far we discussed how to figure out the null hypothesis and the alternative hypothesis according to our research question. And in the following steps for the hypothesis testing, we are going to use the same story. So here, I would like to emphasize that here, I would assume that our students in this course are regarded as the simple random sample from our general population. But of course, that is not true in the reality because this is more like a convenient sampling. It's apparently not a simple random sampling. But just to keep going for the hypothesis testing, so we just consider this result of the simple random sampling. Okay. So far, we mentioned that our null hypothesis is that the average of our students is the same as the average of the population. So in the following steps, remember, you can consider this as the innocent results. We just assume that our suspect is innocent. And in the following discussion, we just assume this is true and to develop the further analysis. So the idea of the hypothesis testing is that based on our null hypothesis, we want to test or we want to see whether our data support our hypothesis or not. So in order to look at results, we need to find what the sampling distribution of our sampling mean. So this is actually the knowledge that we learn from the, I believe it's in a lecture 9, where we can, or lecture 10, where we how to figure out the sampling distribution. So just in case you kind of forget about how we figure out the sample distribution, there's a 3-step procedure. And the first step is always to check whether our distribution is normally distributed. Remember, we have a decision tree, right? First of all, we look at the population distribution. And in our example, we don't know what's the population distribution, right? Because we just say, okay, our population has mean 16 and standard deviation 2.4. So we don't know the general population distribution. So the first decision, we will say no because we don't know like what's the population distribution. And then we look for what's the sample size. Our sample size is actually quite large. It's 144. So in that case, which means we can approximately regarding our sample distribution follows a normal distribution. And remember, no matter what type of the distribution we have, the sample mean and the standard deviation is always the same. So the sample mean is the same as the population parameter. Because remember here, our null hypothesis is that our mean is the same as the general population. So in that case, our mean mu should be exactly equals to 16. And likewise, the standard deviation should be given by the sigma divided by the square root of the n, which is approximately 0.2. So based on this idea, we could work out what's the sample distribution. So we know it's like centered around 16, and it has a bell shape because it's a normal distribution. And then we look at where is our data located in the sample distribution. Because our data is like a 16.57. So if you look it up in our distribution, you will see that it is actually quite far away from the center, right? And this sample distribution tell us what's the probability that we sample our data. So as you can see, the probability of our sample is actually very, very, very small. It's almost, it's a very tiny number. So the what it means is that if we assume our null hypothesis is true, we will get this distribution, right? But based on this distribution, our sample is actually quite weird or quite extreme in this distribution. So either there's the two situations. Either we just so unlucky to sample such a very extreme sample, or our original null hypothesis is incorrect. So that's the idea for this test statistic. So in order to safely tell whether our data is extreme or not, we are going to use the knowledge that we learned in lecture 9, where we're going to compute how many standard deviation away is our sample from the mean of the sample distribution based on the null hypothesis is true. So to do that, which means we're going to calculate the z-score. So the z-score has a fixed formula, right? So it's our value minus the mean of the distribution we have divided by the standard deviation. So in this case, we will get our z-score is 2.8. What that means is that our sample mean is actually far away from the mean of the sampling distribution in 2.8 standard deviation. So that's the idea. So as you can imagine, if it is away 2.8, it's actually already quite far away. And just to quantify how far away it is, we introduced the idea of so-called the p-value. So basically, we are trying to say whether our data is extreme enough. So how to tell whether our data is extreme or not? So we are going to see what's the probability we get even more extreme data based on our null hypothesis. So as I mentioned in the previous slides, we get a z-score which is 2.8, right? So we can approximately regarding it is almost like a 3 sigma, right? 2.8 is very close to 3. So here, for simplicity, we just regard it as 3. And so basically, our statistic is located at 3 sigma away from the mu. So that's the idea for this one. So what's the percentage of our data is more extreme than our current statistic? So this is the knowledge we learned from lecture 9. So to tell that, we can just apply our empirical rules, right? So basically, that will be given up by this region. And remember, our hypothesis is two-sided. So we should also consider this region. Because for this region, for example, if you get a negative 100, it is even this one, although it's negative, but it is actually more extreme than our case, right? So we also need to take this region apart into our consideration. So because our statistic is located as the 3 sigma, so this side we have around 0.15% of the data more extreme than us. And from this side, we also have 0.15%. So in total, we have around 0.3% of the sample that will be more extreme than our data. So in this case, we will say our p-value will be given by 0.003. So there's a question that can we calculate a p-value if the data is not normally distributed? So we usually need to have some assumption. So because here we're using the empirical rule. So I would say in this course, I will say no, we cannot compute the p-value if our data is normally distributed. But in fact, in general statistics course, there is a way to compute the p-value always, because we can use some fancier methods to compute the sampling distribution. But in this course, we just consider no. So if our data is not normally distributed, we cannot compute the p-value because we cannot construct the sampling distribution. So as you can see, the idea is that only 0.3% data is more extreme than our current data set. So which means our data set is already very extreme in terms of the percentage we have. So that indicates that our data is very unlikely to happen based on the null hypothesis. So finally, we will draw a conclusion based on the p-value we just get, because the p-value is telling us how extreme our data set is, right? And we get a p is around 0.0003, which is a very small number, which means only a small proportion of the data or a small proportion of the probability that we will get a more or even weird result than we have right now. So a large p-value means the probability we observe our current data is large. So which means probably our null hypothesis is true, because based on our null hypothesis, we have a very large probability to observe our current data. However, if our p-value is quite small, that means there could be only two situations. The first situation is that we just happened to observe our data in a very small chance. And another situation, probably our precondition is wrong. Our distribution shouldn't be look like this. So which means our null hypothesis is incorrect. So this is the conclusion that we can draw from the p-value. And that concludes the whole hypothesis testing process. So any questions so far about the process of the deciding whether we reject our null hypothesis or not? So there's a question about why we consider that we have mu minus 2 sigma 2. So I guess the question is why we consider this region, right? So we consider this region because so our null hypothesis is whether our sample mean is different from our population mean, right? Because our population mean is somewhere over here, right? So there's two different directions to make it different. Either we are too large, so which is this region, or we are too small, which is also different from our population mean. So what it means is that there's two different ways to make it different. So that's why we need to consider them both. So that's why we consider this region too. So in this course, I won't ask you to calculate the p-value. So this is just the examples to show you like what's the idea of the p-value and why we can draw conclusion just based on the p-value. And in the finals, I won't require you to do this. So you won't compute the p-values, because probably in the future, if you take another higher level stat course, you will come back to this again. So I won't require you to know this, but what you just need to know is what's the meaning of the p-value and what's the conclusion we can get from the p-value. So that is the knowledge just in case in the future when you collaborate with the other people and other people say the p-value of something is something, you won't freak out about the meaning of the p-value. Okay, so there's a question about explain again how to compute the p-value. So here, the p-value is computed according to our empirical rules. So first of all, we need to know like what's the z-score to know like what's the range or what's the location of our data located in the sample distribution. So remember, just now we have 2.8. And for simplicity here, I just regard this 2.8 is equal to 3. That's for simplicity. So if we know that our sample data is 3 sigma away from our mean, so in that case, we can compute the p-value just according to this empirical rules, because the p-value is the the probability that we get a more extreme data than our current statistic. So which means, what do you define the more extreme? You will given by this region, because this data will be, the mean will be even larger than our current one. And this region, the mean will be also more far away from the mean than our current one. So that's why we will sum up the percentage of the data in this region as well as this region. So we will basically sum up the percentage of here, and we get this percentage. So that's the idea for compute the p-value. Now, of course, I won't require you to compute the p-value in final, but you just need to know what does the p-value referring to in this case. Any other question? I understand this part could be quite overwhelming for a beginner of this part. So just don't be afraid of this. Just don't be freaked out. So the take-home message for this part is that our idea of the hypothesis is that we just assume the suspect is innocent. We assume the null hypothesis is true, and then we construct the sampling distribution based on this possibly wrong null hypothesis. And then we look at whether our data set is weird or whether our data set is extreme in our distribution. If our data set is very, very extreme, which is very likely that our null hypothesis is actually incorrect, because we shouldn't expect to get a very weird data, right? So that's the idea in a hypothesis testing. Any other question about the p-value or how to draw a conclusion about the p-value? So basically, a large p-value, we are more likely to believe that null hypothesis is probably true. And if we have a small p-value, that means very likely our null hypothesis is incorrect. The next question is, how do we tell our p-value is large or small? So in reality, or in many statistical research, we usually pick a threshold, the 0.005, and if our p-value is smaller than that, we will say we have a very extreme case, and we will consider our null hypothesis is incorrect. Otherwise, we will kind of accept or not reject our null hypothesis. So here we would give this threshold a name called the significance level. So of course, for some other research, we could change the value of this significance level, but this 0.05 is just a conventional choice. So if our p-value is smaller than 0.05, then we can use the phrase statistically significant to describe our conclusion. So for example, in our case, we will say the difference between the population mean and the sample mean is statistically significant. But here, what you need to know is that by statistically significant, we don't mean that our null hypothesis is definitely true or not, because when we have a small p-value, there are two different situations, right? Either we just get such a extreme data by chance, or our null hypothesis is true, but we cannot tell which case we are in just according to our data. So we cannot tell from our p-value to exactly know whether our null hypothesis is true or not, and we cannot know why we observe such a very extreme data. But what we can learn is that very likely, or statistically, we should believe that the null hypothesis is wrong. So that's the idea. So there's a question about the threshold. So okay, so my mic is a stat. Is that better right now? Okay, so there's a question about um, is exactly 0.05 statistically significant, or is it just smaller than 0.05? So this threshold usually does not take the 0.05 account. And we usually just compare, we actually, we hardly get an exactly p-value equals to 0.05. And in that case, we need to be very careful. But in that, we usually don't take the exact 0.05 into the small p-value area. So we usually consider whether it is smaller than 0.05 or not. So the take-home message for this part is that when we draw the conclusion about the statistically significant, we need to be very careful about the meaning of it. When we say the difference is statistically significant, we are not saying the difference is true or not, but we're just saying statistically, we are very likely to believe that there is a difference. So just be very careful about the interpretation here. And in the independent task, and you will reading a very short paragraph about what's the meaning of the significance here. And you will see that the significance does not mean that our difference is large, but it just means that the probability that we support the null hypothesis. So again, because every test could be right or wrong, and so does our hypothesis testing. So if we figure out the confusion table, just like the beginning of the lecture, we can work out this 2x2 table. So basically, the results of our test could be either we reject our null hypothesis or we don't reject our null hypothesis. And of course, in truth, there could be our null hypothesis is false or our null hypothesis is true. And similar like our false negative and the false positive, there are two different ways to make mistakes in the testing. So here we distinguish these two different types by using the name type 1 error and type 2 error. So type 1 error is just referring to the case where we reject our hypothesis given that our null hypothesis is true. So which means our null hypothesis is true and we happen to reject it. So that's the type 1 error. And type 2 error referring to we just failure to reject our hypothesis given that our null hypothesis is incorrect. So which means our null hypothesis is incorrect, which is given by this column, and we failed to reject that. So that's the type 2 error. So as you can imagine, basically these two errors could represent a different meaning. And that's why we kind of distinguish the idea of the type 1 error and type 2 error, just according to whether we are talking about the true null hypothesis or the false null hypothesis. So based on the type 1 error, we also define the so-called the type 1 error rate, which is basically the percentage that we have in in the type 1 error. So it's the probability of rejecting the null hypothesis, given that the hypothesis is true. So which means we are looking at this column because that's the condition, and we are looking for what's the percentage of the type 1 error in this column. So that's the calculation for type 1 error rate. And we also define the power. So for type 2 error, we actually, that's quite weird. So in statistics, we don't care about type 2 error rate, but we care about the so-called the power. So the power is actually defined as the probability of rejecting the null hypothesis, given that it's not true. So because we are given that null hypothesis is false, right? So our condition is actually the first column. And we're looking at what's the percentage of the rejection. So which means we're looking at the percentage of this cell among this column. So that's the definition of the power. So basically what power means is that given that our null hypothesis is wrong, like how powerful is our test that we can reject that? So that's the intuition for the power. So the power can be influenced by a lot of things. The first is the number of the observation, which is the sample size that can influence our power. So this is actually very straightforward. For example, suppose in a test and there is a calculation question and you get 1 in that calculation question, but my answer key is actually 10. So you're kind of wondering that whether you are wrong or it's just like my answer key is wrong. So basically here, our null hypothesis is that my answer key is correct. So say the actual results is actually 10 and your 1 is actually your sample results, right? So in this case, we only have 1 single sample. So in this case, you are not sure whether whether this we should reject our null hypothesis or not. So you ask your friend, and your friend gave you say 1.5, and in that case, you can calculate the average of the two values to be 1.3. And in this case, you are more confident that probably the null hypothesis 10 is wrong, right? And finally, after asking the whole class, and you get the average to be 1.1, and in that case, you are very, very sure that our null hypothesis is incorrect. So as you can imagine, as we increase the number of the sample size we have, or the number of the observation we have, we are more our test will be more powerful to tell the difference. So that's the idea for this part. And another factor that might influence our power is actually the effect size. So what is the effect size? The effect size is actually the magnitude of the difference of our groups and our expected null values. So for example, in our case, the difference of our sample mean and the population mean will be our effect size. So let's consider two different scenarios. Say under scenario A, we have population mean to be exactly 10. And under scenario B, our population mean is actually 60. So tell me, under which scenario we are more likely to reject the null hypothesis? So remember that effect size is referring to the difference of the population means to our sample mean, right? And so just use your intuition. Under which population we are more likely to draw the conclusion that or to reject our null hypothesis that our sample mean is different. Sample mean is the same as the population mean, which means we can draw the conclusion that the sample mean is different from our population mean. So yes, actually the answer is actually just A. So yes, you are correct. So this is actually just aligning up with our intuition. So if the difference is between the population and our sample mean is too large, then almost every you can imagine if the difference is so large, almost every test can tell the difference of these two. And however, if the difference of our population mean and our sample mean is very tiny, so you can imagine that more tests will make mistakes, and in that case, we'll have for each test we have the less power to tell the difference. So that is you can just get this from our intuition. So in our real life, when we talk about like there's a significant difference, we usually mean the effect size. So like in the real life, when we say our sample mean is significantly different from the population mean, what they mean is that the absolute difference of these two values is large. But you need to keep in mind that in statistics, we are talking about different things. We are not just talking about the difference of these two, but we are talking about after considering our null hypothesis, after considering the standard deviation and the mean of the sampling distribution, these two are still different. So that's the different message from the statistic point of view. Any questions so far about the effect size? Okay, then we will talk about the last issue of the hypothesis testing. So before I talk about the last issue, let's try to compare two different scenarios. Say we have two scenarios, and just tell me like which one you believe is a fair way to do statistical hypothesis testing. So in the first way, we first of all we initiate uh, certain hypotheses. And then we design our study according to our hypothesis, and we're going to collect the data and finally make some analysis based on the data we have. And for the procedure B, we start with the design uh, with our study design and collect our data, and we keep trying to find the hypothesis until that we find a certain hypothesis that is promising to make some interesting conclusions. And finally, we will do analysis and make conclusion based on that. So tell me which one you believe is a fair way to do the hypothesis testing. I see a majority students choose A. Can anyone tell me why you think A is correct? Or B is not a fair way? Anyone can share your thoughts. So actually, I would agree with the students who choose A. So I also believe that A is a more fair way to do the hypothesis testing. In fact, B is more like a cheating, right? Because so for B, it is like we are keep trying to find the hypothesis that will draw the conclusion that we want, and that is basically um, quite similar to cheating. So this problem is actually related to the issue I'm going to talk about, which is the multiple testing. So the multiple testing is referring to that in the same data set, we are trying to draw conclusions of multiple hypotheses. So for example, given our sample data, we want to test whether our sample mean is different from our population mean. And we also want to test whether our sample mean is greater than 5 and whether our sample mean is greater than 10, whether our sample mean is smaller than 11. So you draw a lot of conclusions. You make a lot of hypotheses, and you just use the same data set to help us to do the testing. So as you can imagine, if you make so many hypotheses, and by chance, maybe one of them will be correct. And in that case, we will have some interesting results. But that is not fair because we are kind of like we are kind of cheating in a sense that we are not referring to some specific hypothesis, but instead we are keep try and error and trying to find something that is interesting. So in the scenario A, when we say our data is rare in our sampling distribution, that is real rare because we can see the probability of more extreme than our current case. It's small, it's very, very small. However, for the scenario B, because we made a lot of hypotheses, we actually we made our sample distribution rare, or made our sample distribution rare. So, for example, in another hypothesis, our sample distribution maybe looks located in this place, and in our sample in certain hypothesis, we make it in an extreme way. So that's why the scenario B is not a very fair way to do the hypothesis testing. And the problem for the scenario B is just that we make too much hypothesis. We keep try and error, and that is not fair ways to do hypothesis testing. So in fact, in many study, in the literature, you can see that like a lot of study actually following the procedure B. So that is because the data itself is very expensive. So for a lot of time when we collect the data, we don't want to waste the information, right? So that's why they keep exploring interesting hypotheses. But keep in mind, if you are following this procedure, we need to be very careful about the type 1 error we have, because in fact, our rare statistic it can be easily made. It's not actually really rare, so we can very likely to make the type 1 error. So just be very careful when we're following the procedure of the B. Okay, any question? Okay, so we pretty much getting to the end of today's lecture. So as you can see that the hypothesis testing involves 4 different steps. We start with our hypothesis, and then we collecting informations to create a test statistic and to create p-value, and finally we make conclusion based on our p-value. So the take-home message is that according to our p-value, we can never say our null hypothesis is right or wrong. What we can say is just that statistically we are very confident with our null hypothesis, or we have a lot of evidence to believe that null hypothesis could be wrong. So because for statistician, we never say always, or we never say never. So just be very careful about the interpretation for the significance. And also, you can see that our hypothesis testing procedure can be influenced by a lot of things. So like our study design, our sample size, our effect size, the power, and also even the number of the comparison, which is the number of the testing that involved in our study. So that is pretty much the take-home message for today's lecture. So any question about the content for today's lecture? So if not, I'll briefly talk about the independent study task. So for this talk, you will read 1.5 page article about, it is actually taken from the recommendation book. It is about like the comparison of the real importance and our statistical significance. So it's a very, very short, and pretty sure you can read that up very quickly. And we have one question quiz following up that following up that article. And this is our last independent study task. So which means we won't have any independent study task in the next lecture. Okay. So also you can see that the assignment 4 is out. So you can see there's a lot of description in the assignment 4, but just don't freak out about that, because most of the words are just helping you to understand the website and help you to play with the data. So the question are actually quite straightforward. Okay, and finally about final. So just attention that our final exam is take place in a Sunday, which is December 13th. I don't know why it's a Sunday because I at least for me when I was student, I never take exam during Sunday, but I don't know why they arranged this like this. So for this time, we also have two different approach to have the final. So if you would like to go with Zoom, for all of the students who want to do Zoom, you need to fill in a new form, which is located in the administration tab. Uh, and that will help me to prepare the Zoom portfolio. So the final is also open book in the same way as the midterms. So you can use any materials either online or offline. It's just that you cannot discuss with each other or use the Google link. So we have 45 questions in 2 hours exam. So actually the time per question is actually it's more than midterm. So you probably have more times to work on each question. And the exam will be cumulative. And you can see that the distribution is quite uniform, right? So for each module of our course, we could have a very equal size of the number of the questions. So that's pretty much the information about the final. And so if you if you have any other question, you can just type it in the chat, and I will stay here for answering the question, and you are good to go. And thanks for coming for today's lecture. Okay. Um, could you please upload the study task and the practice question today? Yes, I'll try my best to. So I'll definitely upload the study task today, but I'll try my best to upload the practice question at least before tomorrow. So because I have something to check about the practice question, but I'll upload it as soon as possible. We will be able to have a complete final review practice question. So are you referring to the practice question? So for practice question, I guess I will answer, you can ask the question about the practice question on the forum, and I'll try my best to answer my response over there. So in next lecture, we're also going to have a Q&A section. So you can start preparing the exam as early as possible so that you can ask the question in the next lecture too. So will the question be listed according to the sequence of the lectures? So it won't be listed at the same sequence as the lecture. It also might not be ordered according to the difficulty. So which means when you do the final, if you feel some question is really hard, just skip that and mark that question and just get back later because the final exam will be the question itself will be randomized. So each of the students will see a different order of the question. So just keep in mind that. So what is the final weighted? I believe it's 40%. So even if we did a Zoom proctoring before, we will fill out of the form. Yes, you need to reform. You need to refill the form again. No more practice question for the whole class. So there's a practice question following up today's lecture. And in the next lecture, it's almost like a review, but we just have probably one or two new concepts, and which is very, very simple comparing to today's lecture. So you don't need to worry about that.
Sorry. So basically, for what I'm asking is, will
Yeah.
there be like a complete practice questions like that will prepare us for the final exam? So
So
essentially,
like,
like each little unit practice questions prepared us for the midterms, but will you have like new practice questions to
uh,
prepare us for the final?
no, we won't have the new practice question, but when you prepare in the final, you can use the material of the practice question we have, and also you can use the material in our midterms. So I will ask very similar questions like our midterm, like I would say 10% of the question in the final will be probably with minor modification from our midterm questions.
Okay, thank you.
You're welcome. Any other question about final? Okay, so there's a question about could you go over again why p-value is equals to point? Okay, so it's asking the step 3 of our calculation of the p-value. So to calculate the p-value, you need to know like what is the p-value referring to. So p-value is the probability that we get ours another sample data which is more extreme than our statistic, right? So which means what is the region that we get a more extreme? So it is either greater than our current statistic or it's located smaller than mu minus 3 sigma. So this region is also more extreme than our statistic. So after you agree with that, then we can go to the next step, which is compute the percentage. So we just sum up the percentage of data in this region and the percentage data in this region, and you will get around 0.3%. So our p-value is exactly the same as this 0.3% because it is the probability or the percentage of getting a sample statistic more extreme than our current one. So that's the idea of the calculation for the p-value. Does that make sense to you? Okay, great. Any other question about final midterms or assignments? If not, I'll thank you for, oh yeah, there's another question. Could you please briefly explain the steps of hypothesis test again? Okay. So for this, you just remember our analogy. So first of all, we start from our practice question. Oh, sorry. We start with our research question, and from our research question, we just assume our our initial assumption is correct. So which means we assume that our null hypothesis is true. And based on that, we can, because based on our initial research question, we can formulate the null hypothesis and the alternative hypothesis. And at the first step, we just assume that is true. And then we evaluate, like based on the situation where it is true, what's the probability we observe our current data. If the probability is so small, then we should believe that our initial assumption is probably wrong. So that's the idea. So in terms of the practice, the hypothesis testing will be 4 steps. The first step is corresponding to our the first part in our flowchart, which is to formulate the statistical hypothesis. And step 2 and 3 will be constructing the test statistics and also the p-value to help us to determine whether our whether we should reject our null hypothesis or not. And the last step is corresponding to the last part of the flowchart, which is to draw a conclusion based on the p-value. So that's the general procedures for this hypothesis testing. Okay, if no other question, I will see you again in the next lecture. And I hope you can just start early to prepare the final so that you can bring the question to the next lecture. Okay. See you everyone. Bye.